Hi, welcome back. Today we're going to be talking about exponential growth and decay, and then we're also going to talk about logistic functions. But first with exponential functions, remember that means our variable is in the exponent. And to do all of these problems sort of generally the same, we're going to use base E. So that'll make everything consistent. Now the A is our initial condition. So that's what's happening when X is 0. And K is the growth or decay constant. So it'll be specific to the problem, whether we have bacteria that's doubling every so many hours or a radioactive element that's decaying with a half-life so many years or whatever. But that K is a constant based on the specific problem. Now, if K is greater than 0, then e to the kx is greater than 1. So this will be a growth. Because we learned in our lesson on exponential functions that when the base is greater than 1, it is an increasing function. If k is less than 0, then e to the kx actually becomes 1 over e to the positive k, right? Negative exponents will flip it over. So that means this is getting smaller and smaller. So this is a decay because this will be less than 1. Okay, the graphs, if we have a growth, it'll be going up and it should go through the point 0, A. And if it is a decay, it'll decrease like this and it'll still go through the point 0A. Okay, so this is a growth and this is a decay. Notice they both have horizontal asymptotes of y equals 0. They do have a limiting factor, a lower bound, if you will. Okay, so what does this look like? Well, let's take a problem. Population growth is often exponential in nature. So let's say we had the U.S. population in 1970 was 203.3 million, and it was 308.7 million in 2010. Find an exponential growth function that models the data. So the first thing I'm going to do is I'm going to let year 0 equal 1970. So this is my starting point. So this means I have the point 0, 203.3, and that's going to mean A is 203.3. Okay? Then that means that 2010 is actually going to equal year 40. So I have the point 40, 308.7. So now I know that I have an exponential growth will look like y equals AE to the KT. So my A is 203.3. And then I'm going to let the time be 40. And it's going to equal 308.7. Okay? So now we need to solve for K. All right, so I'm going to get my calculator handy. And the first thing we're going to do is we're going to divide by the 203.3. Okay, this means e to the 40k is equal to this fraction. Okay, now to undo an exponential, what we're going to do is we're going to take the log of both sides, and we're going to use the natural log since it is base e. Okay, what that does is this actually changes this from an exponential to a log, and it tells us that 40k is going to equal the natural log of 308.7 divided by 203.3. So k will be this log divided by 40. So my exponential function is 203.3 e to the natural log divided by 40 times t. Okay. Now I can get a calculator out. Let's simplify this a little bit. First of all, if I have e to the natural log of something, this will just equal x. So this will simplify down to this base of 308.7 divided by 203.3 raised to the t over 40. Okay, so if you want to simplify it, you can. So this is my function though. And then part B says by what year will it reach 335 million? So I'm going to set 335 equal to 203.3 times this fraction, and let's go ahead and see what that equals. 308.7 divided by 203.3 is approximately 1.518446. You want to take it out to a lot of decimal places here in the middle of the problem, otherwise you're going to get a large amount of error since this is exponential. You can simply leave it as the fraction until you get to the end of the problem. Okay, so then I'm going to divide by 203.3. Okay, and I'll get 335 divided by 203.3 equals that fraction to the t over 40. And then again, to get this exponent out of the exponent, what we're going to do is we're going to take the natural log of both sides. Okay, and then what this ends up doing is we end up with the natural log of 335 over 203.3 equals t divided by 40 times the natural log of the 308 divided by 203. Now I can solve for t. So I'm going to multiply the 40 across. And I'm going to divide this other natural log. Now I can go to the calculator and calculate all of that all at once. And what I end up with is 47.8298 years. Okay, now year 0 was 1970. So 1970 plus 47.8 years puts us in year 2017. You know, the decimal point is just going to tell me what month I'm in. But the question is just by what year will it reach that? So it will reach it in the middle of 2017. Okay? So that's our answer. Okay? Sometimes when we deal with this stuff in chemistry class, a lot of radioactive elements have half-lives. That's the amount of time it takes for the element to decrease in amount, like it deteriorates over time. So if we start with a sample of 125 milligrams, that means at time 0, I have 125 milligrams. Its half-life is 50 years. So that means at year 50, I'll have half of 125, which is 62.5. Okay, but this is, because it's decreasing by a half over time, this is going to be an exponential problem. So the 0 time, giving me 125, means A is 125. Then I can use this second point, and I'll get 62.5 equals 125 e to the k times 50. Now the interesting thing is here when we solve this, because it's a half-life, it's going to do exactly what we expect, and that is it will go to a half. So every half-life problem is going to end up in the same form. So I can undo the exponential by taking the natural log, and k will equal the natural log of a half divided by 50. So our k will always be of this form. The log will always be of a half, and the 50 is based on that half-life of 50 years. And then when I go to write the equation, I now have 125 times e to the natural log of a half divided by 50 times t. And if we reduce that, we get 125 times a half to the t over 50. So any half-life problem will have a base of a half, and the exponent will be divided by whatever the half-life is. Now this is the same if we've got a population that's doubling. The base will end up 2, and the exponent will be divided by how often it's doubling. Or if it's tripling, it'll be a base of 3, and the denominator of that exponent will be how long it takes to triple. So they'll always end up in that same form. And so here's our equation. Now it says how long until there is less than 50. So we want this 125 times a half to the t over 50 to be less than 50 milligrams. So we're just going to solve the equation out. So I'm going to have 1/2 to the t over 50 will be less than 50 over 125. 50 divided by 125 gives me 0.4. And then I can undo the exponential by taking the natural log. Okay, that means the exponent will come out to the front. And so I can multiply by the 50 and divide by the natural log of a half. Now, natural log of a half is less than 0, so this does flip the inequality because it's going to take at least that much time for this to happen. And so then we just go to our calculator. So 50 times 0.4 divided by the natural log of a half is negative. Whoops, I have an incorrect value. Hold on. Okay, actually we lost something here. When I took the natural log, I forgot to take it of this side. So I need a natural log here, and I need a natural log of the 0.4. So when I do 50 times the natural log of 0.4, and I divide by the natural log of a half, I end up with 66.096, and this is in years. So it'll take a little more than 66 years for us to have less than 50 milligrams. Okay, so that is this question. Now I did skip this part. Now this is actually the easy part. If I want to know how much after 70 years, I'm simply going to plug in a 70. So I'll have 125 times a half to the 70 over 50. So I plug that in my calculator. and we get 47.366 milligrams after 70 years. Okay. All right, then we have logistic growth models. Now, logistic growth models are always in this form. Okay, so this, in the denominator, this is a negative exponent here, which means this E is a decay. This is getting smaller and smaller and smaller, which means the denominator is getting closer and closer to 1. So the fraction is getting closer and closer to C. Okay, so this value here in the denominator is approaching 0. That's the horizontal asymptote of an exponential. So F is approaching C, so C, it also has this horizontal asymptote across here at whatever C is. In this particular drawing, C was 2. So that is called our limiting factor. C is greater than 0 in these real world problems, and so f of x will also always be greater than 0, and so it has a second horizontal asymptote down here at y equals 0. Okay. All right, so what does this look like? Well, here's a function that describes the number of people who have become ill with influenza T weeks after its initial outbreak in a town. Now, there's only 30,000 inhabitants in the town. So that means that 30,000 is a limiting factor. Okay, no more than 30,000 people can get this influenza this influenza because there's only 30,000 people there. Okay. All right. So for question A, we want to know how many people when the epidemic begins. Well, that's at time 0. So all I do is find f of 0. So I'll have 30,000 over 1 plus 20 times e to the 0. So that's 30,000 divided by 21. And that'll be 1,428.5714. So we'll have 1,429 people. Okay. Now, how many people will be sick 4 weeks later into the epidemic? Okay, so for part B, we're doing time equals 4 weeks. So f of 4 is 30,000 over 1 plus 20 e to the negative 1.5 times 4. So we go to the calculator and we plug that in. And we get 28,582.996, so on. And so about 28,583 people. We can't have a part of a person, okay? And then finally, the question is, what does this limiting factor mean? Okay, well, the limiting factor, we already said, is 30,000. So the function has a horizontal asymptote okay, of the function. But that also means that no more than 30,000 people can get the flu. Okay, so it limits the value of the function. And that's why this is a logistic, not just an exponential. A lot of times spreading of things and growth of bacteria and all of that population growth, we think of it as an exponential because it just keeps getting bigger and bigger and bigger. But here we have a limiting factor, so it ends up being a logistic. Okay, now when we're looking at real world data, sometimes what the objective is to use that data to approximate something else that's going to happen, to make predictions. And so how do we know what type of function to use and how do we find it? So here's what we're going to do. The first thing we're going to do is we're going to go to our graphing calculator, and you're going to go to your statistics menu, stat. If you have a TI 83 or 84, you're going to go to the stat menu, and you're going to edit your lists, and you're going to put this data in as list 1 and list 2. So this is going to be our X, our independent variable, and this is going to be our Y, our dependent variable. Okay, then you're going to make sure your stat plot is on. So you'll go to the second Y equals, and then you're going to graph. Now, when you graph it, you're going to want to make sure your window, you might want to make your Y max of your window equal 100, and you might want to make your X max maybe 15, just so it gets larger than these two so that you see all the data. Now, what does this function look like? Well, if I connect the dots as close as I can, it looks like a log function. Now, I don't know what the base is, and I don't know how it's been moved around, but if I know it's a log function, then I can go back to the stat button, so this is also my stat menu. But this time, instead of clicking edit, I'm going to do calculate, and I'm going to choose option number 9 for LN reg. That's for natural log regression. And when I do that, I'm going to make sure these two lists are the list I entered my data in. Okay, so sometimes you might be having more than just the two lists, and so you might be in L3 and 4. And then if you want to store it, you can go to your vars button to your variables menu and choose a function to put it in, and then just hit calculate. And it'll give you this. So what this means is Y is 31.954, okay, plus 28.9473 times the natural log of X. So if I want to make a prediction of, say, what is it for somebody that is age 15? So this will be approximately 31.954 plus 28.9473 times the natural log of 15. And we could go to our calculator and we would get that it's going to end up being 110%. So that means that between age 11 and age 15, the brain is as big as it's going to get. Okay, we have reached the maximum capacity. So anyway, so sometimes your data points will look like a quadratic. Sometimes the data points will look linear or even exponential. And your calculators, our computers, will find all those regressions for us to allow us to approximate and predict what will happen in the future. So, okay, so hopefully that helps a little bit on our exponential growth and decay. And we will see you next time. Thanks for joining us. Be sure to hit subscribe below.